Okay, so we had a little mini lecture on the kinetic theory of gases. If you haven't watched that, go back and watch that one. What allowed us to look at how the temperature determined the average speed of the molecules in a gas. And that relationship was Boltzmann's constant times the temperature was equal to 1/3 mass times the average speed squared. Okay, and we talked again in that one really about kinetic energy as well. But if we're just interested in, okay, how fast are the particles actually moving? This is average speed squared, but we know in averages some are going faster, some are going slower. So what does that distribution really look like? And so we talk about average speeds in a very specific way, and we're going to talk about 3 ways to think about the distribution of speeds of a gas in like in a container of the gases in the system we're looking at. So the first is if I just solve for this average speed, okay? So I'm going to solve for average speed just in this relationship. So V squared, average V squared, is equal to 3 kT all over m. Of course, if I take the square root, I get the square root of 3 kT over m. This is what is known as the root mean square. Okay? It's the average speed taken as a result of doing that whole manipulation with the average square of the average, right? So we call that the root mean square. So that's one representation of speeds distributed in a gas. The root mean square it's an average of those speeds, but like we said, some move faster and some move slower. So James Clerk Maxwell discovered that the average speeds, or the speeds, in the gas are distributed, okay? And they're distributed through, he did some work and looked at, and we're not going to do that whole derivation in this particular mini lecture, but I want to share with you that there's actually 3 pieces of information that we can pull out of Maxwell's work. One is the root mean square. So that is one distribution of the speeds. It's also that there are certain speeds that are highly probable. That comes out of Maxwell's distribution. And the most probable speed is actually the square root of 2 kT over m. So this is the most probable. And if we take the square root of 2, this works out to be 1.41 times the square root of kT over m. Right? So that's the most probable speed that we see. And we have the root mean square. And then we actually have the true average. And the true average, Maxwell's distribution determined to be 8 over pi kT. Now, I don't memorize these equations, as you know, so I won't make any of my students memorize them, and you can go through that derivation if you would like to. We're not going to at this point. For our purposes, we don't need to. And that's on average 1.73 over m. So we have 3 relationships we can use to describe the motion of the particles. We have the most probable speed that exists, we have the average speed that exists, and then we have the root mean square speed that exists. So 3 different ways to describe kind of that distribution of gases and how fast they're moving in our system. All right, so those 3 ways to describe the speed. Good job.